Hello students, welcome to Concepts of Physics with Irfan. Students, we are going to start moment of couple and then we will cover equilibrium and its conditions. So, moment of couple, couple can be defined as two forces acting on an object having the same magnitude and opposite direction. Okay, and these two forces, they must be acting at two different points. So the two forces must be separated by a perpendicular distance and let's call that distance as d, right? So whenever two forces are acting on an object and if those two forces are in opposite direction and having the same magnitude, and such two forces, when they act at two different points and when they have a kind of perpendicular distance between them, then such two forces can be considered as coupled. So let us take an example that we are having a rod, right, and this rod is of length L. Okay, now if two forces act on such a rod at 2 points, let's say that this point is A and the other end of the rod is B. So a force F1 is actually being acted at point A and another force F2 is being applied at point B. Now as you can see that both these forces, they are acting at two different points and the distance or the perpendicular distance between such two forces, in this case we have called it L, right? So generally we can consider that kind of perpendicular distance as D. Okay, now when these two forces F1 has the same magnitude as F2, then at that time we can consider that such two forces will be known as couple, right? So couple are such two forces having the same magnitude which act on an object in different direction, maintaining a kind of perpendicular distance between one another. Okay, now what does mean by moment of couple? Okay, so because of these two forces, this object, it tends to rotate, right? It tends to rotate. Okay, so this turning effect or this rotational effect of such couple is what we call moment of couple. So whenever a kind of couple is acted on an object and in turn such an object tends to rotate, then this phenomena is what we call moment of couple, right? Okay, and due to this couple, a kind of rotation or torque is produced, and we can even find that kind of torque if this rod, if we pivot it at a point and we call that point O, right? So at that time the perpendicular distance from A to O, let's call it R1. Similarly, the perpendicular distance from O to B, let's call it R2, right? So we are having moment R, right? So these two forces, they can produce a kind of torque in such a rod, and that torque ta would be equal to R1 times of F1, so it is the cross product of R1 and F1 plus R2 cross F2. So the net torque will be because of the individual torque produced due to these two forces, right? So as a whole, we can find the torque by using this expression. So this is how we are going to define moment of torque. Due to a couple, if a kind of rotation is produced, that kind of rotation is what we call moment of torque. Okay, we can take many examples, like if we consider the steering wheel of a car, and I hope that a steering look like this, right? So this is a kind of steering, and if a driver is going to take a turn, so what he is going to do is he is going to use both of his hands, right? And one of his hand is actually applying a force in this direction, and the other hand will try to turn the wheel in that direction, right? So both these two forces, they are maybe they are having the same magnitude, and we can see that there is a kind of perpendicular distance between two such forces, right? And both these forces are acting in opposite direction, and due to such couple, a kind of turning effect is produced, right? So in the perspective of torque, rotation, or any kind of turning effect, moment of couple is important. So it is just the combination of such forces which act on an object, on a single object, but in opposite direction, and when such two forces are having the same magnitude, then we can consider such two forces as couple, right? Here students, equilibrium can be defined as such a state in which an object will be at rest, or it will be moving with constant velocity. So such a state of an object can be considered as equilibrium. So how we are going to define it? The state of rest or uniform motion. What does mean by this uniform motion? So if an object is moving with constant velocity, so such a motion is what we call uniform motion. So the state of rest or uniform motion of an object is called equilibrium, right? Equilibrium, right? Okay, now there may be many type of forces acting on an object, and the net result of such forces turn out to be zero. So we can say that two or more forces can be there, right? Okay, let us take an example. If we are having a box, and this box, it is lying on a table, right? And let's say that the box is stationary, it is not moving. Obviously if it is lying on a table, so it will remain stationary. Okay, so this box, it is lying on a table and it is stationary, so there is no any kind of motion associated with this box. Okay, how many forces are acting on such a box? So right now its weight is acting downward, right? So this will be the direction of the weight of the box, and the reaction of the table will be acting in upward direction, and that reaction we can call it normal force, right? So from free body diagram, we are having two forces, the weight in downward direction and the normal force of the surface in upward direction. Okay, now as this object is at rest, it is not moving, it is not changing its position, so we can say that the object or the box is at complete equilibrium, right? Now for equilibrium, the acceleration of the object in this case it is zero, because if it is not changing in its position, then obviously it will be having zero acceleration. Equilibrium has two special types. The first one is what we called static equilibrium. Static equilibrium. And this is such a type where the object will remain at rest. So when an object is at rest, object is at rest. So from the figure we can see that in spite of two forces which are acting on such a block, the block is not going to change its position. So such type of equilibrium is what we call static equilibrium. So in case of static equilibrium, the acceleration is zero, right? And the velocity is also zero. Right now I am considering the linear acceleration and linear velocity. Okay, the next type we are having is dynamic equilibrium. Dynamic equilibrium. So dynamic means moving, right? So it is such an equilibrium where the object will be moving with constant velocity. So when an object or a body moves with constant velocity, so such an equilibrium is what we call dynamic equilibrium. Okay, so here the acceleration will be zero, but the velocity of an object it will not be zero. Obviously, as it is moving with constant velocity, so we will be having certain value for velocity, right, other than zero. Okay, now dynamic equilibrium can be further categorized into two different types. The first one is translational dynamic equilibrium. Translational, right, dynamic equilibrium. And translational dynamic equilibrium refer to such an equilibrium where the object will be moving in a straight line with uniform velocity, right? So when the object moves in a straight line, or the motion will be linear with uniform velocity, so the velocity has to remain constant. So that is the condition for dynamic equilibrium. So with uniform velocity. Okay, right. So over here again the acceleration, the linear acceleration, because it is moving in a straight line, right? So the linear acceleration will be zero, but the linear velocity of the object will remain constant. Okay, so we can take an example of a paratrooper, right? Let's say that a paratrooper, he is coming down, right? Now as he is moving down, but the velocity of such a paratrooper is not going to change. So he is moving with some constant velocity, and due to this constant velocity we can say that the paratrooper is actually in translational dynamic equilibrium. Okay, what about the other type of dynamic equilibrium? So the next dynamic equilibrium is what we call rotational dynamic equilibrium. Rotational dynamic equilibrium. Okay, as we know that motion itself is categorized into different types, like we can have translational motion, we can even have rotational motion, right? So depending upon the motion we are having, we can have two types of dynamic equilibrium. So the first one was translational and the second one is rotational. So when an object rotates with constant angular velocity, such an equilibrium will be known as rotational dynamic equilibrium, right? Okay, so but here in this case the angular acceleration that we represent with alpha, it has to be zero, the net angular acceleration, right? So it has to be zero. But what about the angular velocity omega? So we will be having a constant angular velocity, right? Example is you can consider the example of a compact disc, right? So when such a compact disc is rotating in a CD player, so it is actually rotating with some constant angular velocity. So you can consider the example of CD, compact disc. Okay, so far we discussed that equilibrium is such a state of an object or a body in which the object will be in rest or it will be moving with constant velocity, right? So when the object is at rest, such an equilibrium is what we call static equilibrium, and when the object is moving, such an equilibrium we can consider as dynamic equilibrium. Now dynamic equilibrium, further we are having two types. Translational dynamic equilibrium, when the object is moving with uniform linear velocity. So such an equilibrium will be translational. And on the other hand, if the object is moving with uniform angular velocity, the equilibrium is what we call rotational dynamic equilibrium. Okay, now as we discussed over here that even if an object is in equilibrium, there can be many forces acting on such an object, right? Now, how we are going to achieve a kind of equilibrium, or how we are going to satisfy the condition necessary for maintaining static or dynamic equilibrium? So, let's move towards the conditions for equilibrium. Okay, dear students, so what are the necessary conditions to maintain a complete equilibrium? So there are two conditions, so we are going to discuss those two conditions. The first condition is what we call first condition of equilibrium. First condition of equilibrium, right? So what is the first condition? Like how we are going to maintain a kind of equilibrium? So the first condition states that the summation of all kind of forces, summation of all kind of forces on an object will be zero. What does it mean? It means net force will be zero. Okay, so what does it mean? It means that if we are having an object, right, and if many forces are being acting on such an object, then for maintaining a kind of equilibrium, the summation of all such forces has to be zero. So F1, let's say this is F2, right, F3, F4. So all these forces are pointing in different directions. So their summation has to be zero. So we can write sigma, that sigma stands for summation of F will be equal to 0. Okay. Or we can even write I start from 1 up to n, because the net force F net, it is actually the summation of individual forces. Let's say if we are having n forces, so we can write F1 plus F2 plus up to, we have to go on till Fn, right? So the summation of all these forces, the net force, must be 0, and this expression can be written as sigma Fi, where I start from 1 and it goes up to n, and this net force is actually 0, right? So whenever this condition will be satisfied, there is a chance that the object will be in equilibrium. So this condition, it can only ensure that the object will be in translational equilibrium. So it can ensure that the object will be in translational equilibrium. Okay, so whenever the net force is acting on an object is 0, the object will be in translational equilibrium. So if the object is already in rest, so it will maintain its state of rest, and if the object is already moving with certain constant velocity, so it is going to continue its velocity, right, that constant value of velocity. But overall the object will be in translational equilibrium. Okay, so it is not going to change its state, right? For translational equilibrium, if I draw 3 or 4 forces, let's say the first one is in that direction, the second one is in that direction, and this is the third one, right? So, and this is the fourth one. Okay, so whenever we draw such forces and add all these forces, then for having a kind of translational equilibrium, we have to get a kind of null vector or null zero value of our force, right? So let us add all these forces. So this is F1, and let's say this is F2, right? Similarly this is, okay, F3, and in order to get 0, F4 has to somehow that much large. So in order to add all these forces, we have to place F4 over here. Okay. Right, so this is F4, F1, F2, F3, F4, even we can have 5 forces, 6 forces. So you can see that, after adding all these forces, we are going to get a kind of closed polygon. Closed polygon. So whenever we get closed polygon, what does it imply? It implies that the net force or the resultant force is actually 0. So we are going to get null vector, right? So that's why we can say that the summation of all these forces is 0, and such condition ensure translational equilibrium, right? This condition, it can assure us that the object will be in translational equilibrium, but anyhow we will be not sure that whether there will be a kind of rotational equilibrium or not, right? So it is not enough for a kind of complete equilibrium. So this condition alone, it is not enough. So there is another condition, that what we call the second condition of equilibrium. And what is the second condition? It says that summation of all torque acting on an object must be 0. Must be 0. So summation of all torque. So if we can say that the net torque is actually equal to 1, let's say there are 3 or 4 or n torque are being acting on an object. So 2, similarly we have to go on up to n. So if summation of all such torque is 0, then we can say that the second condition for equilibrium is satisfied, right? So even we can write in sigma form, sigma ta I, where I start from 1 up to n. So once we will open this summation, we are going to get the expression above, right? This expression we are going to get. Okay, now let us take an example that this is a kind of rod, it is pivoted at this point, right? So due to some applied force, a kind of torque is produced which we call tau1 in anti-clockwise direction, and on the other hand we are having summation of forces at this side, and due to all those forces we are going to get a kind of torque in clockwise direction, and we call this torque as torque, right? This is clockwise. Okay, now for having a kind of complete equilibrium, rotational equilibrium, these two torques, they must balance one another. So we can say that their summation must give us zero value. For that we can write that torque clockwise is actually equal to negative of torque anti-clockwise, or torque anti-clockwise is equal to negative of torque clockwise. So we can simply write that the net torque is actually the sum of torque clockwise and torque anti-clockwise. And when such a summation is zero, it means that the object will be in rotational equilibrium. So when the object will be in rotational equilibrium, then its angular acceleration will be zero, but it may or may not have some constant angular velocity. That again depends that whether the object was initially in any kind of rotation or not, right? So we can summarize these two conditions. The first one is sigma f net. It has to be zero in order to maintain a kind of translational equilibrium. So this is for complete equilibrium. And when the summation of all torque acting on an object is zero, then we are having rotational equilibrium, and when both these two conditions are satisfied, we are having complete equilibrium. So there will be no linear acceleration and there will be no angular acceleration, right? So over here the summation of net forces, it means that the summation of forces along x-axis, along y-axis, along z-axis, all the component must give us zero value, right? So if we are having a kind of coplanar forces, then we can write that, let's say we are having coplanar forces F1, F2, F3, then actually, the summation of Fx along I-axis, it is giving us zero value. The summation of Fy along y-axis, it is giving us zero value, right? Similarly, all the torque clockwise are actually equal to all the torque anti-clockwise. So the summation of all clockwise torque is equal to the summation of all anti-clockwise torque. So we can shortly say that the summation of net torque must be zero for ensuring or for maintaining a kind of complete equilibrium, right? So these were the two conditions necessary for equilibrium. I hope that you can solve problems related with these two conditions. Okay, so in the next lecture we are going to start our next chapter. So stay tuned and subscribe this channel. See you in the next lecture.